Hi, good morning, afternoon, evening, everybody. This is an honors precalculus lesson, an introduction to polar curves. So let's go ahead and get started. Here's our warm-up. Take a look at it, read it. So once you've read it, really, so each of these pink highlighted numbers kind of goes in for one of these things. So radius / amplitude, period, vertical distance from the sun on March 1st, and horizontal distance from the sun on March 1st. So see if you can match. All right. All right, so what we're doing today is polar and rectangular coordinates of polar and rectangular coordinates and graphs. You'll be able to describe the connection between rectangular and polar coordinates of a point in the plane and be able to convert between them. We're also going to explore graphing a little bit and see how much time we have to do all of that. We have warm up, which you just did, framing the learning, polar and rectangular coordinates demonstration and practice. The check for understanding is in the middle of the lesson. And then we'll spend the second half of class on a Desmos graphing discovery exploration. Then we'll summarize and close. You'll need Zoom, Nearpod, Desmos, and maybe highly advisable to use some pen and paper to take notes. We have got new formative and homework this week, and then don't forget about weeks 1, 2, and 3. Those are still applicable. Interims are this Thursday. They're being prepared this Thursday, so please make sure that you have your grades on point where they need to be by Thursday. And we also don't have school that day. All right, so just to frame the learning, why do we learn about polar coordinates and curves? So there are a lot of things in life that orbit. Planets are one example. They orbit in an ellipse. There are things that orbit in a circle. There are a lot of things that are constantly moving that have a radius and an angle to them, and it's more useful to think about them as a polar curve than as an XY line, because the polar curve indicates, you know, how they're moving and the angle of rotation and, excuse me, all that good stuff. So it's handy, it comes in handy to have polar coordinates to measure the instantaneous position of an object in time. All right. So what is a polar point anyway? So it's important to understand that polar curves take place on the same plane as rectangular curves. So if you're in Desmos, right, and you want to graph a polar curve, you go to settings, you can click the grid. You can click the grid. This is like the coordinate regular XY Cartesian coordinate plane. And this is the polar plane, but the same point goes on the same plane. Like if I put in -1, 1 on the polar axis, you'd still have a point at -1, 1. It's just the polar curve gives you the idea of plotting a point as a coordinate point takes different measurements of what's going on at the point. So let's get back to that so I can show you. So here's an example, just an example of a polar point that's also a rectangular point. So you have a point here at 12, 5, right? Your X distance from the origin is 12, your Y distance is 5. So you have a point right here in blue, sort of this blue circle, right? So in our traditional XY rectangular format, we'd say that point is at 12, 5. But in polar form, we go R theta instead of XY. R represents the radius or the distance from the origin. And then theta represents the angle at that point. So again, I really want to emphasize it's the same point, but we measure it as radius and angle from the x-axis instead of x distance, y distance. Same point. 1322.6 is located at the same exact spot as 12.5. Okay. Let's plot some polar points. I think it's a good exercise just to get used to the idea of this new way of thinking about it. So remember, R is the first coordinate in polar coordinates. R is the first polar coordinate. So that would be how many circles from the origin we count. It's the radius. And then theta is the angle, and we can think about it just like we thought about the unit circle, right? So, you know, 0 degrees is on the x-axis, pi over 2 is at 90 degrees, and so on and so forth, okay? If you get a negative radius, you just flip the point 180 degrees, and then with the negative angle, the negative angles, you remember, you measure them clockwise from the x-axis. Okay, so let's get started with 2 and pi over 2. So 2 space, so R is 2. So out from the origin, we go 1, 2. And then pi over 2 is 90 degrees, or, you know, the top of the circle. So we go out 1, 2, and then we plot our point right here. Right, so this is pi over 2. 3, 30 degrees. So we go out 1, 2, 3 from the origin, and then 30 degrees is about here. 30-degree angle, 30, 60, 90. This polar coordinate, I think, is a little bit funny. 1, 2, 3, 4, 5, 6. Yeah, it's divided into 6. So it's not our typical coordinate, but as long as you get it about where 30 is, that's fine. 4, 180. So we go out 1, 2, 3, 4. So that's all the way at the edge of the way this circle works. And then 180 degrees, remember, is all the way to the left, right? 180 degrees around the circle takes us here. And then -4, 180, remember with the negative radius, you just flip the point. So it's basically the same as 4, 180, but we just go 180 degrees, okay, around. So we just flip that point 180. All right, let's do a couple more. So 2 and then -pi/6, so that's 2, -30. So we go out 1, 2, and then down clockwise, pi/6. 3, -45, go out 1, 2, 3, and then 1/8 of the way through the circle right here at 40, -45 degrees. -3, -45, so we just take that 3, -45 point, which we had here, and then just flip it 180 degrees to be in the top left of the unit circle, right? So we had a point at 3, -45, but then if we have -3, we take that point and we flip it 180 degrees. And then +3, 135, so we got 1, 2, 3, and then 135, okay? So one interesting kind of thing to notice is that these two are the same. These are the same location, right? -3, -45, and 3, 135 are equivalent, okay? And so you'll probably notice as we go and plot some more, and especially in your homework and other things, that there are actually 4 ways to write the same polar point. I'm not going to go over them because I'd rather have you kind of figure that out as you plot some points, but because of the nature of a polar plane and because of the circular nature of the unit circle, there are several ways to write the same polar coordinates, okay? Okay, so your turn, go ahead and plot these, pause the video, give it a try. All right, so let's review. So 3 pi/4 about here, 2, 270 about here, -4, 0, that's 4, 0, but flip it 180 degrees right here, and then 4, -pi/6 down here, okay? And then just a reminder, with a negative radius, just flip the point 180 with a negative angle, measure clockwise from the x-axis as usual. Okay, another thing we need to learn is how to convert our points. So remember that the points are the same, they're same location, and we just need to know how to convert them from one form to the other. So if you're converting polar to rectangular, remember polar is in the form radius angle, r theta. The way that you convert it would just be r cosine theta is x and r sine theta is y, which makes sense, right? Because if this is the angle right here, this is your angle, the cosine of your theta would be x/13. So if you multiply both sides of that equation by 13, it would be your x distance, and then the same for y, okay? So if we did 13 cosine 22.6, we get numbers, this is because of rounding, but we get numbers that are pretty close to 12, 12.5. Okay, rectangular to polar, as you might expect, to get the radius from xy, use the Pythagorean theorem. X squared plus y squared equals r squared. So 12 squared plus 5 squared equals r squared, and r is 13. Okay. Just like we had with vectors and parametrics, the way you get the angle is inverse tangent of y/x, right? Which makes sense. Tangent of theta is opposite over adjacent, or y/x. So inverse of that makes sense that that's your angle. You just need to make sure, like we did in vectors, that you check your quadrant, right? You have to add 180 degrees if you know that your actual angle is in quadrant 2, but your calculator says it's in quadrant 4. So just make sure you check. Right, and we can see that when we convert this back, it ends up being 22.6. All right, give this a try. The formulas are here in the red box. So the first one is convert from polar to rectangular form, round your answers to 3 decimal places. Second is convert from rectangular to polar form. What quadrant is -724 in? 1, 2, 3, or 4? Right, this is in quadrant 2. This is in quadrant 2. So if you get an angle when you do inverse tan with this one, make sure you check and make sure that that angle is actually indeed in quadrant 2. If it's not, you got to make sure that you change it. Okay. So here's in review. Check that out. And we're going to do our CFU now. So if you are watching this video and you didn't do the CFU, please email me so you can do it. All right, so now we're going to rock out the Desmos exploration. So now we're going to transition to graphs and looking at graphs. The expectation today is that you stay engaged, that you try the exploration. This is not necessarily going to count against you if you don't understand everything today. We're going to cover it in a little bit more precision on Thursday, but this is a discovery activity. The intention of this is to get you familiar with what different polar curves look like. Okay, so I'm going to kind of pace you through it. All right, so this is not right. Here it is. So polar curves, I'm going to go through this pretty quickly because if you are watching this, you're not exploring it. You might want to pause the video and send me an email to send you a student pace link. But we've got the first slide of this is you have R equals A cosine theta and R equals A sine theta, right? So first we're going to just look at A cosine theta. All right, so here is our slider, right? So we can make A very, very small. We can make A very, very big, right? And just notice what's happening to the graph as you slide A. And then we can click the equation A sine theta, and the slider will affect both of them. So just take a moment to notice what's going on as you play with it. Okay, so go ahead and answer the question, what do these graphs have in common? What do you think they have in common? And how are the graphs different? Write an equation you think matches the graph shown. All right, so now we're going to add, now that we know that A is basically the diameter or the stretch of the graph, we're going to add another parameter to it, which is N. So sometimes people call it NK or something else, but for this activity, we're going to call it N. So here we have our cosine of N theta, and then we also have sine. So you can still slide A, right? You can still slide A and see what's going on. But I want you to also slide N, see what happens. See what patterns you might notice as you slide it. I'm going to uncheck that and check sine. Slide the parameter N for sine. What do we notice? What do we think? Interesting. Okay. And then what do you notice about the graphs? What do you wonder about the graphs? All right, so let's take a closer look at what A does. So we're just going to turn these graphs on and off. Okay, so here's 5 cosine of 5 theta. We see that, I don't know if it's right to call this the diameter, but the length of the petal now, kind of like if this petal was just a squashed circle, 5 is still the diameter of that, right? And then we have these, they're called petals, which makes sense because it kind of looks like a flower. This type of graph is actually called a rose. So if I have 5 petals, my N is in fact 5, right? That's how many petals I have. Okay. What if I have -5? Okay. You know what's interesting, if I look at this, the cosine rose graph, I have a petal that's lined up along the x-axis, right? This goes straight up along, straight to the right along the x-axis. but negative cosine 5 theta goes left along the x-axis. That's kind of interesting. Okay. What if we did 3 and negative 3? Okay. I still got petals, but their diameter is smaller, right? When I had an A of 5 and negative 5, that quote unquote diameter, the length of the petal is 5. But when I have 3 cosine 5 theta and negative 3 cosine 5 theta, diameter is 3. Okay, interesting. Okay, now let's look at the sine graphs. Okay, interesting. 3 sine 2 theta, 3 sine 3, 3 sine 4, and 3 sine 5. Okay, so we see that no matter what, my diameter is 3. And that's, I have straight up A's of 3 each time. Okay, but my petal number is different. 2 theta gives me 4 petals. That's interesting. 3 gives me 3 petals, and they're lined up along the y-axis this time. 4 gives me 4 petals. 5 gives me 5 petals. Again, lined up along the y-axis. Interesting. All right, so how do you think each portion, A, cosine, sine, N, affects the graph? All right, see if you can write an equation that matches the graph shown. You can pause the video and try the problem. What I notice is that if I have an even number of petals, or sorry, if I have an even number for my N, I have twice the number of petals. So let me count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 petals. And my radius looks to be, or my diameter of the petal looks to be about 5. So I'm going to write that this is R5 cosine 8 theta. And I guess I can use the equation editor to make theta there. Or I hope I can I? Maybe not. Yeah, because sometimes they just let you type theta and it converts it, but we can just write cosine theta. All right. Okay, and then an equation that matches this graph. Okay, I've got 5 petals and they're lined up along the y-axis. So I'm going to call that a sine, and then my radius is 1, 2, 3. So I'm going to say this is R equals 3 sine 5 theta. All right. So this next piece is so we've done circles and we've done roses. Okay. This next piece is 2 kind of new shapes, and I think that's all we're going to do is these 2 new shapes. So now we're going to forget about N for a little bit and do these types of graphs. So A plus B cosine theta and R equals A plus B sine theta. And we're going to investigate them in steps. So again, first, we're just going to click on the graphs and slide the A's and see what we notice and wonder now that this is a little bit different. Okay, so we play with it a little bit. What do you notice about the graphs? You wonder about the graphs. Okay, so now we're going to look a little closer. What's the relationship between A and B? So you can kind of click on and off the graphs. Notice what happens when A is less than B. Notice what happens when A is the same as B. Notice what happens when A is more than B. Right? See what do you think? What do you think is going on? All right, so given R equals A plus B cosine theta or R equals A plus B sine theta, describe how the relationship between A and B affects the graph. And then see if you can write an equation that matches the graph below. And then this one. All right, so that's pretty much it. You know, feedback, what did you like about this activity? What did you not like? What would you change? If we have time, you'll make some polar graphs of your own. Okay, but if not, we'll just summarize and close. So in summary, we know what a polar coordinate is and some ways in which we use it. We know how to plot a polar coordinate. We know how to convert one to the other, and we have a general sense of how polar graphs work and some of their types. Okay, so just remember you've got that homework, and don't forget about your weeks 1, 2, and 3. Thank you so much for watching. I hope you all have a great day. And as always, just let me know if you have any questions or concerns or anything like that. And that's it for now.